Do you get nervous when your boss hands you a ticket that's related to some kind of an electrical concern? It may be because your electrical foundation is not as solid as it needs to be. That's okay. We're going to shore up that foundation in this edition of The Trainer, coming up next. Today's edition of The Trainer is sponsored by Motor Age Training Connect, an online video training platform for the automotive professional. If you want to become more comfortable at electrical troubleshooting, there are three key areas that you need to focus on. Number one, how to read a schematic, wiring diagram. It's a lot more than just looking where the wire goes, say from point A to point B, or identifying the components that are in that circuit that you're troubleshooting, but you want to be comfortable understanding what kind of readings you should get in those wires, what those components are doing, what their role is in that circuit. Number two, you want to be comfortable using electrical testing equipment. For most of us, that's starting off with the digital multimeter. And number three, certainly not the least important, you must have a solid understanding of the fundamentals of electricity and electrical circuits. So let's start by talking a little bit about what makes up a basic electrical circuit. The very first thing that we have to have in an electrical circuit is something that we want to do the work. I mean, that's what we're building the electrical circuit for, isn't it? In this case, we're using a light bulb as the example, but we refer to any component that does the work in a circuit as the load. The second thing we need is some type of source for that electricity. How do we get that? Well, that's a little story in itself. We're going to cover a little bit deeper in a moment, but let's just suffice to say for now, we're going to call that our source, which is typically the battery. Some may argue that when the engine's running, it's the alternator that's the source of the electricity for the circuits in the system. I've always used the battery as my testing point, so that's why we're going to stick with that today. Now we need to connect the source to the load, and we do that by providing a path from the source to the load, and then from the load back to the source. We refer to the side going from the source to the load as the positive side of the circuit, and the path returning back to the source as the ground side. Once we've made that connection, we essentially have a working circuit, don't we? The light bulb will certainly light up if I connect it on either end to the battery. But that's not going to be very practical, is it? We also have to have a way of controlling when that light bulb is going to turn on or when that load is going to function. We do that with what we call a control device. Now, the control device can be a variety of things. It can be a switch, it can be a relay, it can even be the driver in an electronic control unit. And it can be located on either side of the circuit, can't it? Now last, we have to have some kind of way of protecting the circuit against an accidental overload. Now, how's that going to happen? We'll just kind of stick in a little tidbit here. How does the battery provide the electricity for the vehicle systems? Well, it's a chemical reaction inside the battery that creates an imbalance. So at the positive side of the battery, there are atoms with very few electrons, or missing electrons to be more precise. On the negative side are an accumulation of atoms that have an excess of electrons. Those that have an excess are trying to shed that excess, and those with a shortage are trying to recreate that balance and gain one back. So what we have is the potential between those two posts, an electromotive potential. And when you measure or put your meter leads, your voltmeter leads, across the positive and negative posts, that's exactly what you're measuring. You're measuring that imbalance, that electromotive potential. If we were to connect those two posts, say with a piece of wire, we would provide a path for those excess atoms to get back to the atoms, or those excess electrons to get to the side with a shortage, wouldn't we? And they would do so really, really quick. So quick, in fact, that wire you attach would probably melt down very, very quickly. That's caused by the current flow through the wire, and we'll talk about that again in a little more later on. But now that I have a path connected, I'm restricting that movement through that load, okay? If I have a section of the path on the positive side anywhere before the load that's going to bridge that gap to ground or make that path back to the battery, well, that's the same thing as putting the wire across the two terminals of the battery, isn't it? And just like we see in the cars, when that kind of a condition occurs, the short circuit, we're going to blow a fuse or we're going to burn the wire. So we have a circuit protection device, in that case, a fuse, fusible link, or a circuit breaker. That will always be on the positive side of the circuit. Now this is going to make you think a little bit, I hope. Here we got a picture of an electronic control unit, or ECM, engine control module, and we also have a picture of a relay. Here's the point I want to make. Remember we said the basic elements of the circuit are, we have to have a load, we have to have a source, we have to have a path connecting the two. Then we're going to add some type of control device so that we can operate the circuit when we want it to operate, and some type of protection device just in case the positive side of the circuit gets to ground when it's not supposed to. What would you consider the engine control module? Is that a load? Is that a control device? Is that a circuit protection device? It can serve more than one role, can't it? So when you're looking at that schematic, like we were talking about earlier, you want to consider when a component like that, what is its role in that particular circuit that you're troubleshooting? Is it the load? Is it a control device? It's the same with the relay, isn't it? The relay has to be energized in order for those switch contacts to close. Well, the part that is energized, that coil, that functions in a circuit all of its own, and it's a load. The part that closes and makes the contact is operating as a switch, and that's included in a whole nother section of the circuit, and it's operating as that control device. I want to share just a brief word on parallel circuits. Parallel circuits I don't worry a whole lot about. Yes, there are parallel circuits on the car, there are series parallel circuits on the car, there are series circuits on the car. But when it comes to troubleshooting, I'm really not focused on what kind it is except for one reason. And that's what is shared and what is unique among the loads, the components that are doing the work on that circuit. For example, if I have a series of lights and they all turn on at the same time, like exterior lighting, for example, if none of them work, then I know it has to be a fault that's common to all of the lights. Are you with me? If none of these work, then it has to be something common to all of those lights. And I can focus my troubleshooting steps right there. If it's something that only one bulb is out, if only one bulb has failed, well then I can look at the parts that are unique to that load. What parts of the circuit, what wiring, what connectors, what switches are unique to that load that's not working. And that's the only reason I need to know whether it's parallel or not. Okay. Before you start shrugging your head and turning off the video, another Ohm's Law presentation. Bear with me, okay? I'm not going to ask you to do any math, but there's no better way to understand the relationship between these elements than reviewing Ohm's Law and understanding what it does and what it means. Let's start with E. The E, of course, stands for volts. And we've kind of covered that a little bit already. What is voltage? Voltage is electromotive potential. It's the imbalance between one end of the circuit and the other. That's what's got to happen in order to get electrons moving, to create electricity, to get that electron flow. This is the force that does that. And there's a lot of examples, some refer to it like water pipes and that kind of thing. I'm not going to do all that because I think that just makes it more confusing. It's electromotive potential. It is the power, if you will, that we need to break away an electron on one atom and force it to grab another one from a neighboring electron. That's essentially electricity, okay? We measure that in terms of voltage. We call it electromotive potential. So what I want you to do is keep in mind that when you're placing your meter leads anywhere in the circuit, that's what you're measuring. You're measuring the electromotive potential between those 2 points of your meter. So if I put it on top of the battery, positive to positive, negative to negative, then I'm measuring the potential between those two leads, and on a fully charged battery, that should be roughly 12.6 volts. If I measure it on one side of the ground at the load, and I go to another point on the ground, well, there shouldn't be any potential there, should there? So I should get a reading very close to zero. We're going to talk about that a little more in a moment. The main thing I want you to try to focus your head around is wherever I place my meter leads, when the meter is set in the voltage mode, is I'm measuring the electromotive potential between those two leads, okay? Next, we're going to move on to I. I, of course, stands for current. Now, current is the actual movement of electrons through the circuit, and we measure it in terms of amperage. I couldn't tell you what the exact number is. It's like something million electrons past a point over a given amount of time. It doesn't matter. I don't care. I just need to understand that that's what that term is referring to. If I talk about current, I'm talking about the flow of electrons through the circuit past any particular given point. Now, for most circuits, your current flow is going to be the same no matter where you measure it in the circuit, and that can be a good diagnostic tool. All right, let's move on to the next item. R. R is easy, stands for resistance, and is defined as the resistance to current flow, anything that causes an obstruction or hindrance to electrons moving through the circuit, okay? That's the load, for one, but that's not the only source of resistance in the circuit, is it? Now, when we look at resistance, it's important to understand that everything in the circuit has resistance. The load certainly has resistance. The connectors have resistance. Switch contacts have resistance. Even the wiring offers resistance to current flow in the circuit. Most of these items should provide minimal resistance to the circuit. The only real source of resistance should be the load. And that's a very important concept to keep in mind. The only real source of resistance in the circuit should be the load. And because it is the resistance in the circuit, that's what's primarily determined the current flow through the circuit. If I'm looking at a circuit that has a problem, if the load's not functioning like it should, it's because something is affecting the current flow through that load. That's important to understand because most of the problems that you're trying to hunt down in the shop are going to be caused by something that changed the resistance in the circuit. Now, a very easy example of that is when we have a blown fuse. That's created an open in the circuit, hasn't it? So what is the resistance now through that circuit? If you measure it with your ohmmeter, you're going to get an infinity reading, aren't you? And what happens if we take and short that wire to ground before it goes through the load? What's going to happen to resistance in the circuit then? It's going to drop like a rock, isn't it? But there's some minor nuances in between those two that can cause you just as many headaches, and those are the ones that you have to learn how to find. But before we go on about how to find them, let's talk a little bit about some rules related to changes in resistance. The first one I want you to understand is that in a series circuit, all the voltage, all that pressure will be used to overcome the resistance in the circuit. Now let's explain that a little bit. Just for sake of simplicity, we have a 12-volt battery and we have one bulb in the circuit. The diagram I've been showing you so far. That 12 volts is needed to push through the resistance of that bulb, to push the electrons through that bulb. Once it's done that, once it's done its job of overcoming that resistance, there should be nothing left on the other side of that bulb. Second rule, in the cases of multiple sources of resistance, the amount of voltage consumed by each will be in proportion to the amount of resistance each source contributes to the total. Whew, that's a mouthful. All I'm trying to tell you here is if there's more than one source of resistance, they're each going to get their fair share of that push, of that voltage, of that potential. And it's not going to be, hey, wait, let me take mine first and then you can have yours next. Things happen in an electrical circuit at the speed of light, so instantaneous for the most part. Let's take a look at an example. Again, the only real resistance is the load. So if I start off with a fully charged battery of 12.6 volts, I should get around 12.4 or very close to that to the load. Well, Pete, what happened to the other 0.2? Didn't we say before that everything in the circuit, everything has some kind of a resistance? The wire has resistance, where it connects to the battery has resistance, where it connects to the bulb has resistance. And what do we say? If there's multiple sources of resistance, they're each going to take their fair share. So those sources of resistance are minimal, very small, but they're going to keep you from getting a perfect 12.6 or whatever you measure at the battery. It's not going to be quite the same when you go to measure it at the load. All right? Now, once that voltage that's been provided to the load, once that's overcome that resistance and it's pushed the electrons through and lights the bulb up, there should be very little left on the other side. In this case, we're using as example as 0.3. Don't hold to that number. It's strictly an example, okay? 0.3 volts. Why is there some left over there instead of a perfect 0? Again, because there are other sources of resistance between the load going back to the battery. The wire, the connection points, anything else that might be in line there. Of course, in the real world, we have the switches, we have the control devices, everything that makes up the circuit is going to have some measure of resistance, very small, should be negligible, but it's going to take something to get through, some voltage to get through that. So you'll always have a little bit left over on the ground side, all right? Now let's take a look at this example. If I now put in a series of bulbs and I apply, again, we're going to keep it even, 12 volts source, 12 volts voltage potential, electromotive potential, applied to that circuit, each one of these bulbs have equal resistance. So based on that law again, multiple sources of resistance are all going to take their fair share. They're going to split that 12 volts up equally. Each one should get approximately 4 volts. Now if we use our voltmeter to measure it, it's going to look something like this. As we move along the circuit with our positive meter lead, with our negative lead at the battery, my first stop will be on the positive side of the first bulb. And I should read very close to what I measured at the battery. Again, we're using this for simplicity's sake, but remember what I said earlier. Everything in the circuit has some resistance. It's not going to be dead on the money all the way through the circuit. Now I'm going to get that 4 volts is going to be used by the first bulb because it's taking its fair share, right? So if I move my meter lead now to the other side of that load, that first bulb, I'm going to measure what's left. 8 volts. Now as a technician, that should tell you right away. If you didn't know about these other 2 bulbs, that 8 volts is telling you that there's somebody downstream that wants its fair share. It could be 1 bulb, 2 bulbs, 3 bulbs, I don't know. But that's just telling me that if I did not get the full voltage drop against that load, there has to be something more downstream. Sure enough, we go to the next bulb, we'll measure 8 going in, 4 volts consumed by that bulb. That should leave us with 4 volts going out. Finally, 4 volts going to the third bulb. Now everything has been consumed by the circuit, just like that law says, and I should have nothing left over by the time I get done. Now I shared with you that everything in the circuit has resistance, right? Some of it's designed to be there. The wiring is certainly designed to be there. The connectors are certainly designed to be there. The control devices, the safety devices, certainly the load is designed to be there. But what happens when something that isn't designed to be there happens to show up? Well, these are the unwanted sources of resistance, and these are the things that are going to trip you up if you don't know how to find them. This is your most common problem with electrical circuits today. There's some type of unwanted resistance somewhere in the circuit that's taking its share of that voltage applied, and because it's taking a share that it wasn't intended to take or be taken, the load ultimately pays the price by not having enough to push all the current it needs to function properly. And it's either not going to work at all, or it's going to work sluggishly, or it's going to be dim, whatever the case might be. Here's some common sources. We've all seen this. A lot of corrosion around the battery. That certainly causes an extra source of resistance. How about connectors that are bad? They overheat and burn. We don't have a good contact there. That's an extra source of resistance. Certainly corrosion, and that corrosion can go way down into the wire. It can be at the connector pins, or it can be in the wire itself. Perhaps someone did an improper repair and allowed moisture to get in over time. that's certainly going to affect the resistance of that wire, and that's going to be an unwanted source that's going to slow current flow all the way through the system. Now, how are you going to find that unwanted source of resistance? Don't go run out to that car that's sitting in your bay with your ohmmeter in your hand, because you're never going to find it. Here's what I want you to understand. There's a difference between static resistance and dynamic resistance. There's a difference between what a circuit can do when it's not working and what you're going to see in the circuit when it is working, when current's actually flowing through the wire. And here's how I want you to think about this if you're not quite understanding what I'm saying. Imagine for a moment the positive battery cable running from the battery to the starter. We all know that's a pretty good sized cable, don't we? Why is it so big? You might want to ask yourself. Well, we know intuitively that it's big because it's going to pass a lot of current through it. When I hit that starter, that's going to draw 100, 200 amps. So I need a nice heavy cable to carry all that current. And I'd agree with you, you do. But if you take your ohmmeter and you measure one end of the cable to the other, what kind of reading are you going to expect to get? A few tenths of an ohm? That's about right. Now I'll challenge you. Take that brand new starter cable and extract just one single strand of wire out of it and measure it again with your ohmmeter. You're going to measure about the same thing. That's because there's no current flowing through it. It's a static measurement. Would you take that one strand of wire and connect it between the battery and the starter and expect it to hold up once you hit the key? Of course you wouldn't. So if we want to test for that extra source of resistance, and we're looking for that thief, no matter how big or small he might be, we need to do it dynamically. The first thing that you might want to do to get comfortable with this is to see what voltage drop looks like for yourself. And if you're working in a shop, that should be very easy for you to do. Just get yourself a battery, a couple pieces of wire, and an old light bulb, and wire it all up. Do what we did here. Measure what's going in, 12.4 volts, and then move that same meter lead over and measure what's coming out. You should get a very small amount. Now, your numbers won't be exactly what you see here. First, I want you to measure the voltage at the battery so that you know what you're starting with. Then measure at the positive side of the load. That's going to give you an idea of how much extra resistance is along the path going from the battery to the bulb, but you should be very close to what you measured at the battery. And then go to the ground side. Again, you're not going to be a perfect zero because we don't live in a perfect world. There are other sources of resistance still to come. So you're going to measure something on the other side, a few tenths. Now, some of you may have already kind of guessed what I'm working myself up to here. Some of you may be kind of scratching your head and wondering what I'm talking about. Let's see which group you fall into. I want you to take a close look at this picture. Notice the reading on the multimeter. It's on the voltage scale, of course, and it's measuring 11.5 volts. The meter leads are placed, the positive meter lead is on the altmeter case or ground, and the negative meter lead is at the negative battery post. If you know why this meter is reading 11.5 volts and what that's trying to tell you, well, then you don't need to watch the rest of this video. If you are not sure, you have to think about it, stick around. We're going to explain that. I'll tell you something next. Voltage drop, or learning the voltage drop testing method, was a challenge for me. And I spent a lot of time doing some of the things I'm sharing with you today until I got comfortable with it. But I'm still not 100%. Sometimes I still have to step back a moment and ask myself, what exactly is that meter trying to tell me? And I use that example I just showed you to get techs to actually think about just how comfortable they are with this testing method. I get a lot of people shaking their heads, so if we're shaking yours just now, don't worry, you're not alone. So let me see if I can clarify it for you and make it come to life. Let's start off with the diagram that we started with earlier. Now the negative meter lead is where? At the negative battery post. And we're going to leave it there. I'm just going to use the positive meter lead to test along the circuit. And when I put that positive meter lead down and the meter gives me a reading, do you remember what I said you're going to be reading? You're going to be reading the electromotive potential between your two leads. That's voltage, electromotive potential, okay? If I go and place it at the positive side of the bulb, before it's actually gone through the bulb, then I should measure what? Do you remember what I said earlier? it should measure right about the same as what I measure at the battery directly. I'm going to lose a little bit because there are sources of resistance between the battery and that bulb. So I don't expect a perfect match. Within a few tenths, though, is what I should see. And then I also told you that if I now take that meter lead and I move it over to the ground side, well, that bulb, it should be nice and lit nice and bright. That bulb should have used all that voltage to push the electrons through it. So it's going to use it up. There should be very little left on the other side. Again, we had 0.3 in our examples, but it doesn't actually have to be that number. But it's only going to be a few tenths. There are still things along the way back to the battery that it's still got to push through, right? So you with me? If you want to test this for yourself, remember that circuit I asked you to make earlier? Add another bulb to it. We're going to classify that second bulb as our source of unwanted resistance. So what do you think is going to happen if I measure the voltage coming in on the positive side of the first bulb? It's not lit. I should still measure what I showed you in the block diagram earlier. Pretty close to what I have at the battery. When I go past it, though, am I going to read next to nothing like I would expect? No, I'm going to read something, aren't I? Because there is another source of resistance yet to come. Voltage is split proportionally among the resistances in the circuit. I don't know what the number is yet. I can figure it out using Ohm's law, but I really don't care. What I know is I should measure something here because there is a second bulb in the system. Back to the example. I don't have an extra bulb wired in, but I'm measuring negative at the battery, and the positive is measured just on the other side of the load. So somewhere between that and the battery is another source of resistance, isn't there? And that's why I'm reading that 11.50 volts. There's something between the case ground and the battery negative terminal, which means probably something in the harness, the cabling, that's having an extra high source of resistance that's preventing that all that voltage to drop just across the alternator, right? So very, very important to understand that this reading here is telling me there's a big problem, and it's located where? Between my two meter leads. Now let's talk about the steps to performing a voltage drop test. First thing I want you to do is set your meter to read DC volts, and then place your negative meter lead on the negative battery post as close to the battery as you can get and keep it there. This is vitally important. You have to check the entire circuit, and if you're going to try to make a voltage drop test and you're working at the back end of the car, don't use a frame ground or clip it to the trunk or anything like that, because now you're leaving out a whole huge section of the path back to the battery, aren't you? You're assuming that that's okay, when in fact that may be exactly where your problem lies. So instead, make yourself up a 20-foot test lead so that you can get from one end of the car to the other. Number 3, use the positive lead on your meter to take your measurements. Number 4, be sure the circuit you're testing is on. This is also vitally important. There has to be current flowing through the system in order for you to take a dynamic measurement. Otherwise, you're just taking a static measurement. This means that if you're testing the horn circuit, somebody's got to push the horn button down. If you're testing a brake light issue, then somebody's got to step on the brake pedal. And if it's something that a system is only functioning when the engine's running, well, then the engine needs to be running. Okay, now that you understand the steps, here are the 3 tests I want you to take, and I'm going to guarantee you that when you're done, you're going to know what side of the circuit has a problem. Number 1, measure the system voltage of the battery. Number 2, measure the voltage at the positive side of the load as close to the load as you can get. And then number 3, measure the voltage present on the ground side of the load as close to the load as you can get. Now again, I want you to remember this. You want to get as close to the load as you can to take your measurements. This is not always practical, but keep in mind that if you spot a difference, you have to account for the part of the path that you did not test. All right? So just keep that in mind. Remember, your meter leads are only measuring the potential between the 2 leads. So if you leave a section where you didn't place those leads, well, again, that could be where your problem lies. You must test the entire path. Okay, now let me share with you some examples of the meter readings you'll see and what they mean. First, when you take your first test and you're measuring the voltage at the positive side of the load and you read 0.0, perfect zero, then you're looking at an open on the positive side of the circuit. If the positive side tests normally and you move your meter lead now to the ground side and read a perfect zero, well, now you have an open between the test leads or in the load itself. Now again, let me give you an example. Let's say that you're trying to test the fuel pump and you set up your leads at the connector as close to that tank as you can, but of course you've got the leads running from that connector through the tank and then into the tank to the pump. So this is what I want you to understand. In between the test leads, if I have 12.4 going in as far as I can go, but then I go to the other side and I'm reading a perfect zero, well, somewhere between that last test point, through that wiring, into the tank, to the pump, and then back out to the connector where I'm testing, that's where the problem lies, and that's where I have to go next to isolate where the fault is occurring. If your readings on both the positive and the ground side are normal, then odds are there's a mechanical fault in the load. Okay, that's not quite the same thing as having a blown bulb. What I'm referring to here is if you're testing, say, a fuel injector, and you're looking at the electrical integrity of the fuel injector. It tests good, but the injector is not working. Well, it's not an electrical problem then, is it? It's a mechanical one. Next, if you're measuring the same thing at the positive side of the load as you did at the battery, and you move your lead over to the ground side of the load, and again measure the same thing that you got at the battery, two possibilities. Either the circuit is not on, there's no current flow, or you have an open on the ground side, somewhere between the load and the negative side of the battery. If you get a reading anything other than battery voltage at the positive side of the load, lesser, that few tenths of a volt, then you have a source of high resistance on the positive side. You know, I've been to a lot of classes and I've taught a lot of people over the years, and the question always comes up, Pete, what's the spec for voltage drop? How much is okay and how much is not okay? And I've heard different versions of this myself. I tend to go by current flow. The more current a circuit's allowed to carry, the more drop you're going to be able to get away with, okay? But with that said, I want to share this with you. In my own personal experience, I have never had a source of unwanted resistance cause a change of only a few tenths. Typically, it's a marked change. It's a couple of volts. And you're going to see that on your meter. So don't hang up yourself over just a few tenths. If you see something like this, 6.1 volts, instead of the 12.4 you're expecting to see, that's a problem. You definitely have a problem between your two test leads. Same situation here. The reading I get at the positive side is normal, but on the ground side, it's reading other than just a few tenths. Same as I said before, and in fact, this is the more common of the two. Most problems occur on the ground side of the circuit. Anything that you get over that few tenths, it's going to show up. Believe me, if there's a problem there, it's going to show up. So don't get yourself hung up on just a few tenths one way or the other. Okay, so how do you find the problem once you determine which side of the circuit it's on? That's very simple. Just like these guys are doing between their points of the circuit, they're shortening the path. You know your problem is between the two meter leads. Let's just say with the ground side example. I know it's between the ground side of the load and the ground side of the battery. Well, using the schematic, I'm going to look for the next easiest place to trace or test somewhere in between the two, a connector, if you will. I'm going to take another reading there on the ground side path. If my meter returns to normal, then I know I've passed the problem. And now I go back the other way until I narrow it down to where that point is finally located. So let me say that again. If I have a problem in the circuit between these 2 points, my first step is to find a point somewhere in the middle and move my meter lead closer to that point and measure again. If I'm getting the same reading, the same abnormal reading, then I know my problem is still between the two test points, right? But if my meter reading returns to normal, I know I went past it. So now I'm going to have to back up a little bit until it goes bad again. And then I'm just going to go back and forth until I narrow down exactly where the source of the problem is. Again, use points that are easy to get to. There's no need for you to start pulling seats out of the car and unwrapping harnesses, not at this point in the game. Usually the problem is going to be located near an eyelet, near a connector, something along those lines, or where somebody's made a mistake. You know, they've pinched a harness between a component, whether it's a seat rail or they put the engine back in and pinched the harness between the transmission case and the engine. A lot of things like that can happen, and you'll get to that. But in the beginning, look for common points, easy points to get to. As long as it's between your two original test points, you're just breaking that down into smaller and smaller chunks. Let's take a look at a fairly easy example. BMW backup lamps, one is operational, one is not. Okay, what does that tell me as a technician? Normally they're both on, and they would be wired in parallel, wouldn't they? So if that's the case, I'm going to focus on the parts of the circuit that are unique to the one on the right rear. That's where reading a schematic comes in. And then I'm going to start my tests, just like we just described. I measure the source voltage at the battery first, and then I'm going to measure directly at the load. On the positive side of that left rear backup bulb, I measured a perfect 0 volts. Ground side, I also measured a perfect 0 volts. Where's the problem, and what kind of problem is it? Well, obviously I have an open circuit, don't I? I should be reading at least 12 something here at the bulb going into the bulb on the positive side of the circuit. So I know I have an open circuit on the positive side of the circuit for the left rear backup bulb. Now I can go back to my schematic, again look at the unique portion of that to go further with my tests. So between what I learn on the schematic and what I know about the car, I can easily come up with the next place to test. This harness is passing through the trunk lid and back into the body of the car. That's a high wear area, isn't it? So let's start there. I'm going to look at the hinge side, the trunk lid side of the harness first. Taking another measurement, I get the same reading. Have I passed the source of the problem yet? No, I'm still measuring an open circuit. So let's move on a little closer to the battery from there. Now I'm going to the trunk side of that connector. And now I'm measuring 11.87. It's not perfect, but it's certainly not 0.01, is it? I've passed the problem. So somewhere between where I am now and where I was last is the source of that open circuit. There you go. Broken wire, easy fix. Now I realize that this is a very simplistic example, but if you're new or you're not comfortable with voltage drop, these are exactly the kind of tests that you want to take using this method so that you do become comfortable with it. The first thing I want to stress is that you go ahead and you set up that makeshift circuit of your own using a battery and a couple of bulbs and do the measuring among them so that you can see the different readings that you get and get comfortable with what the meter is trying to tell you. Then you can start applying it to simple diagnostic problems, and then from there you can move on to the more complex. Now that you've had a chance to experiment with that for a little bit, I want you to consider this. I've shown you a very fundamental way of doing voltage drop, and it works very well. There's only one problem with that test method. Sometimes it can confuse people by the meter readings that they're getting, and sometimes if there's a changing voltage, like you might incur while you're actually working on a running vehicle, that too can kind of mess you up a little bit. So I'm going to show you a way now that you can get rid of all that. We're going to start off with the method that I showed you for testing the positive side of the circuit. Again, I told you, put the negative meter lead on the negative side of the battery, use the positive meter lead to check the positive side of the load first, right? So here's only one change I want you to make. To make it even easier for you to use voltage drop as a testing method, I want you to make one small change to the method that I just showed you. When you're testing the positive side of the circuit, just move your negative meter lead over to the positive side of the battery. Remember, testing the positive side of the circuit, both my multimeter leads need to be on the positive side of the circuit. Testing the negative side of the circuit, both my meter leads need to be on the negative side of the circuit. I'm still measuring the voltage potential between the 2 points. But now, since they're both on the same side of the circuit, there should be none, or there should be very, very little. In fact, you can even set your multimeter on the voltmeter scale, set it to millivolts. Why? Because generally I like to use about a half a volt as my go, no go for voltage drop. Most meters have a limit of what they'll read on their scale, and that's usually 300 to 500 millivolts. So if I set it to millivolt scale and I get an OL or a blank screen or the little dashes, that's telling me I can't measure that much, there's a problem. And you can use that on either side of the circuit. So let me say again, if you really want to know if you have a problem or not and you're using voltage drop as a testing method, all you've got to do is remember, on the positive side of the circuit, the meter lead should be on the positive side of the circuit. If I'm testing the negative or the ground side of the circuit, then my meter leads need to be on the negative side of the circuit. Whew. I think we've covered quite a bit today on Trainer. That's all the time I got, but I'll look forward to seeing you again next month.